Hello everyone, join me for Acids and Bases Past Paper Questions Part 1. Let's jump right in, but if you haven't subscribed, please make sure you subscribe now. I will link the paper in the description box down below if you want to do it with me and then unpause and mark. The first question says 8.1, consider the balanced equations for the reaction of water with nitric acid and ammonia below. So they give me two balanced chemical equations. First question, define an acid in terms of the Lowry-Bronsted theory. Now remember we spoke about how we can define acid in terms of two different theories, Arrhenius and Lowry-Bronsted. Lowry-Bronsted is the easier one to remember out of the two. It's a definition, you need to study it. And we've got an acid is a proton donor. It gives away a proton. 8.1.2 says write down the formula of one conjugate acid-base pair in reaction 1. Now, be careful, they say formula. Please don't write out the word. That's why formula is in caps letters. We only need one of the pairs. You could give me two maximum, but we only want one in reaction 1. I'm going to do both of them just in case, depending on what answer you gave me. Now remember, I just wrote the reaction a bit bigger. To identify the conjugate acid-base pairs, we need to first identify what the acid is and what the base is. The easiest way to do this is to link them up. So you can see that this H2O looks like it became H3O+, and we'll discuss how it did that now. And HNO3 looks like it became NO3-. Now you need to ask yourself, how did this become this? What happened to HNO3 to make it become NO3-? It looks like it lost an H. It looks like it lost an H+. In other words, it looks like it donated an H+. So that means that HNO3 is my acid. Okay? And what did it form? What did it become? It became NO3-, which is therefore my conjugate base. So again, how do I know that this is an acid? It looked like it donated. Remember, acids are proton donors. It donated the H. That's why it's gone now over here. So the green ones are one pair. The other pair, so that could be one pair, one option of an answer. The other option could be the yellow ones. H2O became H3O+. So what did H2O do in order to become H3O+? It had to have gained an H. In other words, it had to have accepted an H+, which means that H2O is a base. It's a proton acceptor. And when it accepted that proton, it became H3O+, which is therefore my conjugate acid. And that's why it's called acid-base pairs. Acid forms conjugate base, base forms conjugate acid. Right, my next question. Is the solution formed in reaction 1 acidic or basic? Remember, another word for basic is alkaline, and they want us to give a reason for the answer. If you take a look at reaction 1, what happened when HNO3 reacted with water was the production of hydronium ions. And I remember telling you in my playlist that as soon as you see hydronium ions, you need to think of an acid. So there's your reason. It's acidic, hydronium ions formed in water. Next, you're asked to define the term ampholyte, and we've spoken about ampholytes before. Ampholytes are substances that can act either as an acid or a base. It just depends on what it's reacting with. They then want a formula, note again, not name, formula of a substance that acts as an ampholyte in the reactions above, and they want us to explain our answer by referring to the role of the substance in reaction 1 versus reaction 2. So remember, ampholytes can act as an acid or a base. So basically we're looking for something that in reaction 1 or 2 it's acting as an acid, and then in the other reaction it's acting as the base or the acid, vice versa. So if you look at reaction 1, do you see a substance that is repeating itself in these reactions? I'm looking at water. Water's in reaction 1 and water's in reaction 2. There's nothing else actually that overlaps between the two reactions. So, I think water is the obvious answer, but you need to be able to explain why it is water. So let's consider water in reaction 1. In reaction 1, remember we said that water was the proton acceptor. It went from H2O to H3O+, meaning that in reaction 1, it accepted a hydrogen and it became H3O+. So in reaction 1, water was a base. it accepted the H plus or the proton. And if you look at reaction 2, so in reaction 2 we went from H2O to OH minus, 2 hydrogens to 1 hydrogen. So what happened is water looks like it was a proton donor. It looked like it got rid of a hydrogen, meaning that in reaction 2, water was an acid. And that would be how you would explain your answer to 8.1.5. Now they're starting to give me, variables. 100 cubic centimeters, concentration, another concentration, calculate volume. So we're heading into stoichiometry. As you know, stoichiometry, or the quantitative aspects of chemical change, features in acids and bases. I have a whole study guide on stoichiometry if you want to check out the links in the description box below. But let's go through 8.1.7. So they say 100 cubic centimeters. You need to know, when you read cubic centimeters, you need to know that that is a volume. So 100 cubic centimeters of HNO3 nitric acid of this concentration. So they're giving me volume 100 cubic centimeters. We generally convert that to cubic decimeters by dividing by 1,000. So it's 0.1 cubic decimeters. And they give me the concentration of 0.2 moles per cubic decimeter. As soon as you see moles per cubic decimeter, you know that we're dealing with concentration. And then they say what they do is they take this original solution. So let's say that's in a beaker. We know the volume. It is, let's say, little markings on here. Let's say it goes up to 100 cubic centimeters. That's what it measures in the volume. That's the volume. They give me the concentration of the solution in there. Then what we do is we dilute that solution, and it's now giving me a new concentration, 0.16 moles per cubic decimeter. They want to know, calculate the volume of the water that must be added to the initial solution, to this concentration, in order to get it to this concentration. So this tests our knowledge on concentrated versus dilute. And that is a very important concept that you need to understand. Remember, acids or bases can be concentrated or they can be dilute. And how we work out concentration is it's the number of moles divided by the volume. Now, what it means to be concentrated versus dilute, it all depends on the amount of volume, or the volume of the solvent. So the water, for example, that we're adding. In this case, it's water that we're adding. So if I add a bigger volume of water, if I add more water, then my solution is more dilute. It is less concentrated. If I have less water, so if volume is smaller, less water, then my substance is, or my solution is more concentrated. So essentially what we're doing is we're taking something that is more concentrated and we're adding more water. And the bigger the V gets, the more volume of water, the smaller the concentration gets. So that's basically the relationship that we're working on. What is very important to remember is that we are not manipulating N. We're not changing the number of moles of the solutes. So N stays the same when we are doing a dilution question. The only thing that we are changing is V. The bigger the volume, the more water I add, the smaller the concentration, or vice versa. So essentially what happens is we have scenario number 1, which I'm going to call before the dilution, and scenario number 2, which I'm going to call after dilution. Remember, I have the volume and the concentration before the dilution. When I have C and I have V, so look at my formula. I have C, I have V, I can work out N. So we're going to work out N, which is the number of moles of the solute, and that's going to be before the dilution. But as we just said, the number of moles does not change. So whatever moles I get for before the dilution will be the same as after the dilution. Then once I have the moles after the dilution, consider this formula again. Once I have the moles after the dilution and I have the concentration after the dilution, I can work out the new volume after the dilution. Once I know the volume after the dilution and I know the volume before the dilution, if I subtract those, it should give me the amount of water that I added during the dilution. Think about it. If I know the volume before, Okay, and I know the concentration helps me to get moles. The moles are the same. That's just a rule when we do dilution. I can use those moles and the new concentration to help me work out the new volume. That's the new volume after I've diluted it. That new volume contains the water I added in and the original water. So if I take the volume after the dilution, whatever the V is that I get here after dilution, and I minus the volume before the dilution, I will get the volume of water that must be added. So step 1, I'm going to work out the moles before dilution using the following formula. Remember, C is 0,2, N is what I'm looking for, and V, you must convert to cubic decimeters, is 0,1. So these are the concentrated moles. In other words, before the dilution. Now remember, this is before. Now after the dilution, so after I added in the extra water, we use the same formula, except now I know N, it's 0,02. V is what I'm looking for, and C is the new concentration, 0,16. A silly mistake that I often see students making is solving for V. When your variable's at the bottom of a fraction, it swaps places with whatever on the side of the fraction. So it's 0,02 divided by 0,16. That's how we solve for V. And I get 0,125 cubic decimeters. Now remember, this volume is after I dilute it. So this is the diluted volume. I've also got the volume before I diluted it, 0,1. So how much did I add? Well, you take the after volume, 0,125, minus the before volume, and you get 0,025 cubic decimeters. There's another formula that you can use to do this concentrated and dilute questions. This is not on the formula sheet. It's more of a common sense formula based on a bit of theory that I taught you, that the moles of the concentrated solution is the same as the moles of the dilute. And remember this formula, C equals N over V. How do you get N by itself? You take V over, so it'll be C times V equals N. So how do you work out moles of concentrated? It's concentration of concentrated multiplied by volume of concentrated. Okay, so that's for the concentrated solution. Then for the dilute solution, it's concentration of dilute solution multiplied by volume of dilute solution. So how we would do the question that we just did is you would take the volume of the concentrated solution and the concentration of the concentrated solution, and then you would take the concentration of the dilute solution, 0,16, and you would work out what V is. You would multiply these two together and divide it by this. And you would get the exact same answer. Just remember your unit. Very, very important. 8.2 is the last part of this question. It says zinc oxide is insoluble in water, so it doesn't dissolve in water, can be harmful to the environment. Nitric acid, however, can neutralize zinc oxide. So remember, neutralize means it completely reacts with, in this case, and it says calculate the mass of zinc oxide. So we want to know the mass over here that can be neutralized by 80 cubic centimeters of nitric acid. So that's the volume. I hope you recognize that's volume. And this is the concentration. So they give me volume and concentration of nitric acid. They want to know what mass of zinc oxide do I need to neutralize this nitric acid. And then they want the name or formula of the salt. So let's focus on 8.2.1 first. So this is a normal stoichiometric calculation. They give me information about this over here, nitric acid. They give me the volume, which is 80 centimeters cubed. As we said, we need to divide or convert that to cubic decimeters, divide by 1,000, 0,08 cubic decimeters. And they give me the concentration, 0,16. We know that we have information about this one, but I need to work out the mass of this one. So you do normal stoichiometry. You convert first to moles of nitric acid. Once you have moles of nitric acid, you use a mole ratio to get moles of zinc oxide. So moles to moles in a mole ratio. Once you have the moles of zinc oxide, we can work backwards to get mass of zinc oxide. So that is the process that I'm going to follow. So first step, convert the information given to moles of nitric acid. So we're going to use the formula C is equal to N over V. It's always good to just let the examiner know, or your teacher know, what you're calculating the moles of. So you can see I use this little subscript to tell my teacher I'm calculating the moles of HNO3. You substitute your values in. So 0.16, I'm looking for moles, volume is 0.08. So I get 0.0128 moles of nitric acid. That is what is going to be neutralized. Now remember, my ultimate goal is to work out the mass of zinc oxide. So I'm going to do a mole ratio to get from this part of the equation to this part of the equation. So the two substances that are in my mole ratio, HNO3 to ZNO. That is a 2-to-1 ratio. And if you forgot where to get the ratios from, remember it's the big numbers, the coefficients, 2-to-1. So I know that 0.0128 moles of HNO3 will react. How do I work out how many moles of zinc oxide will react? Well, how do you get from 2 to 1? You divide by 2. So I need to divide the number of moles here by 2 as well. Another thing that I also do for ratios that I've mentioned before is you divide on the side, you times on the top. So 0.0128 divided by 2 times by 1. So I know that therefore 0.0064 moles of ZNO will be produced, or will react, will react. I want to know the mass though. I know the moles, I want to know the mass. So my final step is to convert it back into mass using this formula. You need to write your formula first to get you a mark. Then what we're going to do is in the place of N, I'm running out of space, so it's going to get a bit messy. In the place of N, I put my number of moles. So it's 0.0064. I'm looking for mass. And where do I get big M from? It's the molar mass of zinc oxide from the periodic table. And it is 81. So you take the molar mass of zinc plus the molar mass of, or the atomic mass of oxygen. 16 plus 65. That's where I get that from. Then to solve for mass, we say 0.0064 multiplied by 81. My calculator says it is 0.5184 grams. You may, of course, round that off to 2 decimal places, 0.52 grams if you want. You can just leave it like that. Now, where do you get your marks for this? Well, in this question, you get your marks for formula, substitution, using your mole ratio correctly, formula and substitution, and your answer with units. In order to write down the name and formula of salt X that forms during this reaction, I just want to remind you that this is an acid reacting with a metal oxide. Remember, when it's an acid reacting with a metal oxide, your products are going to be a salt, which we need to figure out what the salt is called, plus water. Remember, CO2 is also only a product if your acid reacts with a metal carbonate, but this is not a carbonate, that's an oxygen. Okay, just a reminder. So how do we figure out the salt? The best way to figure out the salt is to work out what my two reactants are going to break up into. In other words, what ions they will break up into. So what we've got over here is we've got zinc and we've got oxygen. We know that the oxygen ion is O2 minus. Therefore, in this case, it must be Zn2 plus. Plus 2 minus 2, that's where this neutral product comes from over here. Over here, we've got NO3 minus. You need to know that the nitrate ion is an NO3 minus 1. And then the H plus ion. Okay, now remember, acids are proton donors. This is going to be donated to the base. And basically what happens is this and this, part of those two join in order to form H2O. Okay, I know it is weird and you're like, but ma'am, that's one H and in this formula it says H2O, but that's why we balance. Okay, we basically need two of these, which is what the balanced chemical equation says anyway. So we need two of these, which means it would be two of those and that's where water would come from. Okay, then what is left over? Remember, acids are proton donors. The H plus is going to be donated to the base. These yellow things will join up to form the water. The stuff that is left over will form the salt. I've got Zn2 plus and I've got NO3 minus. So Zn has a charge of +2. We figured that out because we know oxygen's charge is -2. That's how we know this is +2. And then NO3 has a charge of -1. Again, we figured that out because we know H has a charge of +1, so this one must have a charge of -1. You can also just learn that nitrate has a charge of -1. Remember, when we put chemical atoms together like this, when we're doing our naming, this must equal 0. Does 2 minus 1 give me 0? No, I have to multiply this by 2. So it's going to be Zn. Did I multiply this by anything? No, so it's just Zn. Then NO3, what did I multiply it by? 2. That is not obvious, knowing how to do this. So it's very, very important that you go over this carefully and understand. So read the question again, write down the name and formula. This is the formula. So we've done one part of the answer. We've written down the formula. What is this thing's name? This thing's name is zinc. Zn is zinc. And NO3 is nitrates. Very, very important that you read your question carefully so you can get the name and the formula. I hope that this was a helpful question for you. Please let me know in the comments down below what else you'd like to see from me in the future. Can't wait to see you in another video very soon, everyone. Bye!